Hi everyone, today we will talk about the bending and shear effect in simple beams. So today's learning objective, after this lecture, it's expected that the student to calculate the shear and the bending moment in any cross section in a simple beam. Student can draw shear and bending moment diagrams of simple beams using the equilibrium method and understand the relationship between load, that's applied load, shear, and moment. Then we will review exam 2 study point. Okay, let's start. So first, let's talk about the beam classification based on different supports. So look at the first one. Look at A. It's a simple supported two support. The right end is a pin joint and left end is a roller. So this is the determinate beam. And B is a continuous supported three or more supports. So for the first part, the right segment, this segment is similar as type A. Then we continue to concatenate a roller, a segment of beam, and a third beam, and end with a roller. So this is also to multiple segment of the beam. It's still a determinate beam type. And C is a cantilever beam. The left side is a fixed end, and right side is free end. It's also the determinate one. And D is the overhanging one. Different from the type A, it has some actual cantilever part here with a free end on the right side. So it's also a determinate type. And E and F, they are indeterminate beam type. And the degree of E is 2 because the right side have the pin joint, that's 2 x and y direction, no moment, and left side is moment. The fixed end, it have 3 constraints. So that is 5 minus 3 equilibrium equation we can list. So that's the degree is 2. Similarly for the last one, F, the both end have 3 unknowns, minus 3 equilibrium equation. So the degree of indeterminacy is 3. Okay, so let's continue. As in our previous lecture, we talked about use the equivalent concentrated load to substitute for distributed loads. And the equilibrium, the location of this equivalent concentrated load is the centroid of the load areas, and the magnitude is of this equivalent concentrated load is equal to the area under the load distribution. However, when we talk about equivalent, this term actually is not equivalent for everything. It's only the equivalent only indicates the equivalent reactional force and moment. That's most focused on the support constraint, like this one and this one. Also, if they have any moment on these two ends, that should be equivalent. However, this concentrated load will cause totally different internal bending, shear, and deflection. So we cannot simply use the equivalent concentrated load to help us to calculate the internal strength. So the follow-up question is, if the equivalent concentrated load approach is not applicable for the internal stress and deflection calculation, which method should we follow to calculate the internal bending, shear, stress? Now let's look at the method we talk about today. So before we talk about that, and let's review what we have learned from our previous lectures. We first talk about the geometric shapes. So if we use the same materials for the same area of the cross section, the different shape of the cross section will give us different resistant capability to hold or to resist the applied force. For example, the H shape, this shape, has the most powerful capacity compared to the rectangular, the square cross-section shape. And on the other side, this side we also talk about some key parameters or characteristic, like the central point and also the moment of inertia. And on the other side, we talk about the material. If for the same cross-section geometric shape, if we use different material, so for different material, they will perform or reflect or show different stress and strength relationship as shown in this diagram. So that's we talk about the parameter, which is, for example, the Young's modulus, which is the linear slope before the elastic period. So by compare these two, when we apply the applied loads, we can calculate or determine the internal stress as well as the deflection of each individual cross-section areas. And this internal stress and the deflection are used to resist to applied loads and keep the beam in equilibrium state for each or for any cross-section areas. So in this lecture, we will only talk about how to calculate the internal stress. After talk about this, we can continue and talk about how to calculate the deflection in any given point. So there is another term we need to talk about is what is the load diagram, shear diagram, the bending moment diagram. So this diagram help us to give us an intuitive or visual representation for each given cross card or section card. So for example, in this point, if we look at this point, the shear, this is the shear diagram, is 0, and the moment is the maximum, the positive maximum. So what is the diagram means? The first is the load diagram. Actually it is essentially the free body diagram of the beam with solved support or constraint force. The reason we only have By here is because this distributed load and the concentrated load, all of them are vertical directed. For the Bx is equal to 0. So in this diagram, we only use By to substitute for this joint and for Ay for this roller joint. And the shear diagram, the shear diagram shows the transverse shears along the beam length. That's vertically in this direction for each cross cut. And the moment diagram are graph. This is the moment diagram, is the graph of the bending moment along beam length. So let's look at for each individual cross section what it looks like. We give some sign convention for shear, bending, shear and bending moment. To help us when we calculate something, we need to have some default positive or negative sign as our default setting. For example, usually for the moment, for the moment direction, the anti-clockwise we view them as positive, and the clockwise we view them as negative. So that's the default setting. So first let's look at the shear diagram. For the shear diagram, the shear at each cross section, the section card, is considered positive when the portion of the left side of this section card tends to be in the upper position when compared to the portion to the right side of the section card. For example, look at the first one. The first one, if it's a cantilever beam and left side is fixed, and right end we have a concentrated load P. So based on our intuitive impressions, if we have a card in between, in a card have an imaginary card here, and this is exaggerate drawing, you can find if we applied a P towards the downwards on the right end, compare the left side of the section card and the right side of the section card. The left side should be a little upper, and the right portion should be a little lower. So that means this shear in cross section AA, in between here, AA is positive. And similar for this one. This is positive. And this one, we have the P applied to the left end, and right end is fixed. And this is and that means if we look at cross section BB, also like this free body diagram, and the left portion should be lower and right portion should be a little upper. So this is a little exaggerate here. So that means this shear is negative. Similar for this one. Then next we talk about the sign convention setting for the bending moment. So look at the example A, and if we have applied force in the middle, go downwards, then the beam has a deflection like a concave upward, which can hold water. This shape can hold water. And if we look further or look into the cross section or in the fiber of this material in a micro level, the upper fiber of the material should under compression, and the bottom fiber of this material of this beam should under tension. So in this case, we view the moment of the moment diagram should be the positive one. So this is a little different compared to the anti-clockwise or clockwise moment for the applied force, because this is related to the moment diagram and the moment stress. And for the right side, the C and D, if we apply the force on the right end, and that's the free end, and the left side is fixed, then the upper fiber of the material is under tension, and the bottom fiber of the beam is under compression, and this show up a concave downward curvature, and which can shed the water down flowing downwards. So that means we define this shape as a negative moment. Okay, so this is just a definition of whether it's positive and negative. So let's look at this as our following calculation setting. And for some bending moment, if we look at this example, we have two concentrated loads on each end, and in the middle we also have another distributed load in between. So in this case, this called overhang beam exhibits a changing curvature that result in this. For example, this is a shed water shape. It's a concave up or downward. This is negative, and then go to, so this part is positive. We continue go to negative, positive. Oh, so this side left side overhang side portion. This is a concave downward. Is negative moment that in the moment diagram. And then from here to here, it can hold water. It's a concave upward curvature. Can hold the water. It's positive. And then this part we go downward. It's negative. So it changed from negative to positive and then to negative again. Okay, so this is just some examples here. And this is just exaggerated deflected shape due to loads on an overhang beam. Now let's go to the next topic is how to calculate the shear and moment diagram. We call this first the equilibrium method. So that method, the main idea of this method is we have some imaginary card, like the method of cross-section when we calculate the truss structure. So we have some imaginary card, and then by cut into several pieces, we can view each piece as an individual, draw the free body diagram of individual segment, and then to list the equilibrium equation. Best by solving this equilibrium equation, we can calculate the shear on the moment in the cross-section area, and then if we want to calculate the stress, we can divide it by the cross-section areas. So the idea is like this, and the visual impression is, for example, this one we have A and the support A, Y, B, Y, because all the loads is vertical directed, so AX is 0. And we cut two pieces, two cross section DD between A and C, and EE between B, C and B. Then for each card, or each one, we can look at their cross-section area and then calculate the V and M. Okay, so some students may ask why we only have, for each cross-section card, why we only have the shear of internal force and the moment. We don't have the tension or compression horizontally. So the reason is like this. If we look at this cross card, section card at this moment, and we zoom in, have a big picture here. Since it's the downwards P here and upwards support reaction here, so this shape between A and for this the deflection, the shape of this beam will have a positive, the moment shape deflection, that is the concave upwards shape, which can hold water, that kind of shape. So that means the upper fiber of the material is under compression and the bottom fiber of the material is under tension. So it looks like this one. And if we in between there is a 0 point with no compression, no tension. So that also called a neutral axis. So if we look at the first very close to piece, this is compression force stress, and this tension stress. You can notice that these two, the magnitude of these two are the same, but only the opposite direction. That means these two internal stress can combine can form a couple of force, a force couple, which has only the pure moment. But then by combine this one and this one, also the third force couple, these two and these two, the force couple, and continuous, So these multiple force couples sum up finally to a pure bending moment only, without any tension or compression force, the sum of force. So that's the meaning. That's the reason why it only have the shear. We only need to draw the calculate the shear and the moment, the bending moment for the beam. Maybe in the future we talk about other structure system. It may have the tension and so they cannot sum up to a final pure bending moment only. But at this moment we only talk about simple beams. So that's the reason we only draw the shear moment diagram and the bending moment. The V diagram, that's the shear diagram and the moment diagram. So is that clear? Okay, let's continue. Let's look at the first example and then to understand how to calculate the V and M step by step. So this is the overhanging beam, and then we draw the free body diagram for the entire structure. And based on the equilibrium equation, for example, based on reference D, we can calculate the sum of the moment equal to 0, and we can get RB, the support reaction at the point B, the vertically RB, is positive 25K, and then list another equation because X direction is 0, and that means dx is 0. Then we look at the sum of y direction, the Fy equal to 0. We can get Rd equal to 5K positive. This is the first step. It's just to use our previous knowledge to calculate the reaction force. So once we have the reaction force, we look at the need to have some imaginary section cut between AB, BC, and CD. That's called the cut E, cut F, and cut G individually. Then let's start from the first one, the section cut E. So if we look at the section cut E, we have a cut here, imaginary cut, and cut this beam into two pieces. The first piece is AE, next right piece is ED. So we give this VE upwards and ME clockwise, and then we list the equilibrium equation. Because X direction is already 0, there is no applied force in X direction. We only have Y direction. The sum of the force in Y direction should be 0. So for this one, it's negative 10K plus VE equal to 0. So VE is positive 10K. Then we list the moment based on the point E. That's the sum of the moment based on the reference point E equal to 0. So we have 10K times X. X is the distance between A and E. So this is the anti-clockwise based on the reference point E. This is the moment is anti-clockwise, so that's positive. For ME, we assume is clockwise is minus ME equal to 0. Therefore, ME is equal to 10 times X. So at this, because the cross-section cut E is between A and B, so the X value is the range of X is from 0, which is close to the A point, far away to B, that is X equal to 5 feet. So this is the first solution for the internal moment and internal shear between AB. Then we jump to the next one. We have a cut in F. So we look at F and look at the left side is AF and right side is FD. We look at AF. Then we list the equilibrium equation for Fy, VF equal to 15K And similarly, for the moment of m equal to 0, we have mf equal to 15 times x minus 125. So at this moment, the range is between 5 feet to 10 feet. So because it's starting from B, that's 5 feet, and until C, it's 5 plus 5 equal to 10 feet. Then we have this problem solved. Then we jump to the next one to see the section called G, like this one, free body diagram. And similarly, we have sum of Fy equal to 0, sum of M based on the point G is equal to 0. Then we have mg is equal to minus 5x plus 75. And this because the G chord is between C and D. So that's from 5 plus 5, 10 feet. And at the end of the D, that's 15 feet. So then we can start to draw our V diagram and M diagram. But one thing you need to pay attention is, when we draw the V and M, whether it's positive or negative, it's not depend on the our calculation. It's based on our sign convention we talked about in our previous slides. For example, what's the sign direction, sign convention between AB? If we look at the AB segment, we have downwards concentrated loads 10K applied to point A. That means that if we have a card somewhere here, the left side should be lower than the right portion, the remaining right portion. So that means the sign convention for the left portion is negative. So that is the reason is negative 10K instead of the 10K we solved here. We solved this positive because we think it's along the y direction. So just pay attention to the positive and negative is not exactly the same as when we calculate the sign positive or negative, whether it's go upwards or downwards or anti-clockwise or clockwise. So they are totally different two sign convention system definition. So, and similarly for the moment diagram, M diagram, instead of the first one is minus 10x, this one, because we have a moment applied downwards, and if we have a card here, so the deflection of the AB segment should be like this. This is a concave downward curvature which can shed water downwards. So that means the moment signal sign is negative. That's minus 10 times x. Instead of the solution we solved is 10 times x. So just pay attention to this one. There are two different sign system. So maybe it's a little confused, right? So we will continue emphasize this thing until you get familiar with this sign convention setting. Now let's look at the example problem 2. It's equilibrium. Also use the equilibrium method. So before we look at this, we can sum up the process to calculate this such V diagram, the shear diagram, and bending moment diagram. The first step is we need to calculate the reaction force at each individual joint. And second step, we need to cut the we need to have some imaginary cut in between, and for each cut we can divide the beam into two separate portions or segments, and then list the equilibrium equations to calculate the internal shear and the internal moment. Then we draw this. Then we draw the diagram into entire beam length to generate the whole complete V and M diagrams. Okay, now let's start to solve the problem 2. This is a beam on the distributed. That's a normal uniform loads, distributed loads. So first we calculate A and B. The vertical reaction force is omega W divided by 2, and also for the point A, it's also this number. Then we look at the section card at C, and look at the left side. We assume MC is anti-clockwise, and the VC is downwards. Then we list the Fy, the sum of Fy equal to 0, and the sum of the moment based on the C is also 0. And the distance between A and C is x. X from 0 to half of the length of the beam L. So that means the section card C is between A point and between middle of this beam. We list the equation for Fy, list the equation for MC, and solve the problem. The VC is a linear equation related to x, and M is the second order. That's the second power of the polynomial equation of x. Parabolic. That's also we call it a parabolic shape of the related to x. The moment equation is the quadratic, the second power of x. Now we continue to look at the calculation of D and write the sum of Fy equal to 0 and sum of the moment based on the point D is 0. And we get V is also a linear equation related to x, and also for moment is also a quadratic. The power of x is 2, and this curve, and x this end, the DD is moved from the middle of the beam to the end of B. So that's a range from half of the L to L. Then we draw these two piecewise segment and find the shear is a downward slope of the line here, and the moment look at a quadratic concave curve on downward shape like this is the moment diagram. So you can find for the uniform or distributed loads, the curve is more difficult than the concentrated load. When we calculate the V, the shear and the moment in simple beams, as long as we look at the concentrated loads, we need to have a cross-section card between two neighboring concentrated loads. But if for the distributed loads, actually we only need to cut one time. For example, for this one, we only need to cut, if we know this pattern, we only need to have one section card, that is C, and the range, the x range should be from 0 to L. So that's enough. We don't need to cut C and have another card D and to prove they are the same. Okay, so that's some pattern you can memorize to help you just draw the minimum section card to complete the entire piece of the V diagram and the M diagram. Okay, the last piece for the bending and shear in simple beams in today's lecture is we want to find some interesting findings or observations. That is the relationship between the load diagram, that's a free body diagram for the applied force, the shear diagram, and the moment diagram. Then the purpose to do this is, based on this relationship, when it can help us to double check if our diagram we draw is correct, because they must have some relationship between these three diagrams. If they are consistent to each other, they fit this relationship, that can help us to confirm our calculation or drawing is correct. Otherwise, it can help you to find some potential errors. You can revisit or resolve the problem, help you to find some calculation errors somewhere. Okay, so let's look at one by one. So the define is V is the shear at the left side, if we look at this segment, and V plus delta V is the shear at the right side, and in between they are applied by a distributed load here. So delta V indicates the change in shear between sections 1 and section 2. Since the beam element must be in equilibrium state, and the equation for sum of Fy equal to 0, let's give these equations. Then we solve this equation and get delta V divided by delta X equal to minus omega. And the shear on the beam between the points x1 and x2 result in V equal to omega times the delta X. And then we put V2 minus V1 equal to omega times the difference between x2 and x1. So this equation tells us one observation for the V diagram is the change in shear diagram between section at x1 and x2 is equal to the areas under the load diagram between the sections 1 and 2. And then we follow the same thing to look at the moment diagram and write down the equilibrium equation for the moment. And then we get this diagram, and you can see the rate between the difference of moment and difference of the coordinates of x1 and x2 is equal to the shear. So this equation states that the change in moment between any two sections 1 and 2 is given by the area under the shear diagram between corresponding sections 1 and 2. So what it means, let's look at the entire. So we follow this one and continue to look at the interesting observations. We find that, look at this one. So this is the V diagram, this is the M diagram, this is a diagram of slope, theta, that's a deflection of this beam, and this is the Y, that's a vertical deflection of this beam. The shape, the change in shape looks like this, and this is the theta, looks like. That's a tangent curvatures for any given point here. Okay, so you can find the omega, the load omega. So that means the slope of this line, the slope of this line is equal to omega. And then look at the moment. And the moment, the slope of the moment is equal to V. That means the V equal to the first derivative of the changing rate of the slope of the moment diagram. And similarly, the moment is equal to the first derivative of the slope, theta, times some coefficient EI. E is the material related modulus, and I is related to the cross-section geometric shapes. That's the moment of inertia. And the theta is equal to the first derivative of y, deflection. And the last one is deflection. You can find, if we put it in this order, and then from the lower one, the bottom, the second one's slope is equal to its previous diagram, and the moment first derivative, the slope rate change is equal to the same given point of the value of v, and the theta, the changing rate of the theta is equal to m, and the changing rate of the deflection is equal to theta. So they have such relationship, and to help you to double check, if you draw this V diagram and M diagram, if you look at both, for example, we look at this point. This point we have this point is flat. That if we draw a tangent curvature for the middle, the top is the top point, the apex. The apex point, the slope of theta is 0, and you can find the V diagram. This value of the V is 0. Okay, that's the same. You can use this way to help you to double check whether your diagram consistent or their relationship follow this pattern. If it follow this pattern, that means your calculation is correct. Otherwise, you need to go back to find some calculation errors. And this the last of these slides we will talk about, give you some mathematical background pre-knowledge. That's the basic curves and their properties. So they divide by 0 degree curve, that's y equal to c, this diagram. First degree, that's the slope. Second degree, that's a parabolic, like this one. And the third degree is the power of x 3. Power x is 3, and y is polynomial equation like this curve. And for 0 degree curve, as we can see this curve diagram in our example problem 1, this curve may represent a uniform distribution of load or the area of a shear diagram. The second one is the first degree curve, that's a slope line. This first degree curve may represent the triangular loading, the area under the shear diagram for a uniform load, or the area under the moment diagram for a concentrated load. This one is the second degree curve, usually represent the area of the shear diagram due to a triangular load distribution, or it could represent the moment diagram for a uniform load distribution. So for this, you don't need to memorize these three. Actually, in our future, in our future calculation, in order to make our drawing process more efficiently, we will have some tabular format, and each basic loading piece will have their related V and M diagram, and you can look up this diagram and quickly find what it looks like and then add them together. So we will talk about this later to accelerate our drawing process. So this class at this moment, we only need to focus on the understand the calculation process and drawing process for example problem 1 and example problem 2. So that's the key piece for this lecture. So next lecture we will continue to talk about this topic. And exam 2 is next Thursday, November 1st, from 1:30 to 3:20 p.m. still in our classroom. closed ball, closed nodes. And if there are any necessary equations or parameters, I will provide it in our exam sheets. So so you need to bring your calculator. Smartphone are not allowed to be used. Now let's go to our study point. So for our study point, I already upload to our Blackboard. Let me show you. So if you go to the Blackboard, this class, coursework, the folder is exam folder. There is the last one is exam 2 study point. Okay, let's look at this one. So compared to our first exam, the study point only have 9. I highlight a calculation. We have totally 3 calculation questions. So let's look at the calculation question first. The first one is determine the overturning stability and bearing the soil bearing pressure of the gravity retaining wall. So this is the same question as assignment 7, problem 3.58 with a few number changes. For this one, the whole solution I already give you in our on Tuesday's class. So if you leave class earlier, make sure you need work on this one, or you can discuss with your classmates. Make sure you understand how to calculate these two. And also the detailed information can be found in our lecture notes. And the second calculation question is calculate the shear stress. Oh, for this one, the equations needed, I will provide the equations which you need, but you need to understand how to use the equations and which parameter indicate which value. You need to select the corresponding values into the equation. The second calculation question is to calculate the shear stress in single or double bolted connections. So that's a similar question as example problem 4 and 5 in lecture 13. It's quite easy for this equation calculation, so make sure you understand how to use the equation. And the third calculation question is to calculate the stress and the strain under thermal effect. This is the same equation as assignment 7, problem 5.18 with I will change some numbers, but the problem statement is exactly the same. So I will give the equations, and you need to make sure you know how to use the equation. And for each individual letter, you need to know the meaning, physical meaning behind this equation. This is 3 calculation question. And another one I highlighted is the drawing question. So this is ask you to draw the Mohr's circle and find the principal stress and the maximum in-plane shear stress. This is exactly similar style to the in-class exercise on Tuesday's class. You need, as you draw, I asked some students drawing the Mohr's circle on Blackboard on Tuesday class. If you forgot the detailed information, you can look at the step-by-step instruction in slides 21 and 22 in lecture 15. So it's pretty easy as long as you know how to draw this. So make sure you just prepare to draw some circles and then to look at the solution in the example. Make sure you understand if I give you a scenario, you know how to use this parameter and to put these values into find the circle, the center of the Mohr's circle, and find any point of this along this circle, and then to determine the radius and also the maximum and minimum stress, and also the maximum in-plane shear stress. Then for the remaining question, it will give you as the choice question. For example, the first one is to calculate the moment of inertia of the cross-section with complex shapes. So since the centroid point question we already examined, we already checked in your exam 1. So in this exam, I will give you the central point for this complex shape, and based on this central point and also the equation, I will also give you to calculate the moment of inertia. So you need to make sure you know how to use this equation and put the correct number into this equation to calculate the moment of inertia along the x-axis or y-axis. Second one is distinguish different types of retaining wall. So this one is similar to, let me show you the lecture notes. Retaining wall, I think is, which one? Okay, this one. So for example, I draw four pictures. I will ask you which is the gravity wall. So you need to know, okay, this one is the gravity wall. If I ask you which is the cantilever wall, so this is the cantilever wall. This is anchor wall. This is the pivoting wall. So you need to know to distinguish the different retaining wall. Okay, this is the first. This is the example for this one. Now let's jump to study point 4. Calculate the stress and strain on the different types of forces. That's a similar question as example problem 1 to 3 in lecture 13. So it's pretty easy and quite straightforward. Just quickly look at them and how to use the equation to calculate them. So that's enough. Then for next one, understand the stress and strain diagram and some significant points. This is also a choice question. It's quite similar to our in-class quiz 2. If you cannot remember, just look at the stress and strain diagram on slide 31 in lecture 13. Lecture 13, this one. 31, let me see, it's close to the end of this. Okay, this one. You need to know, if I ask you which point is the allowable stress, then you need to look at this point. If I ask you which is the ultimate stress, so that's this one. Okay, also this diagram is similar. Okay, so that's this question talking about. Next one, calculate the shear stress. Oh, this is a calculation question. Already talk about drawing question. And the last one, jump to this one. Calculate the shear and bending moment in any cross section in a simple beam. This is the choice question similar to example problem 1 in lecture 16. So that's what we already talked about in today's lecture. So make sure you understand how to calculate the this curvature. Okay. So that's all for today's lecture. So if you still have any, you can quickly look through the study point and talk with your neighbors. Make sure you understand each of them. If you still have questions, you can shoot me email anytime. I will make sure to reply your email as soon as possible. And then you can also talk with me on our Tuesday's class next week. Because we have the exam on Thursday, right? Okay. So have a good weekend. Thank you.